We invented this clock as a fun solution to a problem we will one day have when humans colonise Mars. It has 131 individual components and is a completely mechanical device. One of the first features you might notice about this clock is that it has no hands. Instead, there are rotating dials, each of which represents a planet viewed from above its north pole. Unlike a traditional orrery, which displays the orbital paths of the planets, this clock shows how the planets spin on their axes, which is the motion that creates days and nights. This opens up the possibility of some interesting questions that this device will be able to answer for us. For example, how long is a day on Jupiter relative to Earth? Or, right now, is the Perseverance rover in daytime or in nighttime? Of course, a computer model based on observational data can tell us this information to a great degree of accuracy, but there's something about a mechanical device that helps us to visualise how the system works, plus it's just more fun this way. The dial markers display longitude. 0 degrees is the prime meridian, which on Earth goes through Greenwich in London. The Martian prime meridian goes through the centre of a small crater called Ares 0. But Jupiter and Saturn are gas giants, which makes things more difficult. We can use visual observations from the equator or from a different latitude, but different latitudes spin at different speeds. For our model, we chose to use what's called the System 3 reference frame, which is based on the magnetosphere and reflects the rotation of the planet's core. To depict the planets, we decided to slice and grind some stones with similar colours and patterns that we see on the actual planets. We don't own any lapidary equipment, so I made use of what I had: a cheap tile saw, diamond stones, sandpaper and a water-cooled grinder designed for sharpening woodworking tools. When cutting the stones on the tile saw, you may have noticed I had to get my fingers quite close to the blade. Just to be absolutely clear here, under no circumstances should this be replicated with a toothed blade, and even with a relatively safe grinding blade like this, it really is bad practice. So I chose to glue Mars to an arbor because it was quite fiddly to hold safely. Mathematically, gears are very interesting because, if you're clever about it, it's possible to accurately reflect the complex relationships we observe all around us with a surprisingly small set of gears. Designing a gear train is all about ratios. If you have 2 gears, one with 10 teeth and the other with 20, the 10-tooth gear needs to rotate twice for each rotation of the 20-tooth gear. We can do the same thing with each pair of planets. Jupiter spins around 2.5 times for each rotation of Mars, so we give the Mars gear 2.5 times as many teeth as Jupiter. When Hazel originally came to me with this concept, she had designed a gear train to model the relative rotations of every planet in the solar system with just 17 gears. But we're not just theoreticians, so of course we had to go ahead and build it. But a mechanism with 17 gears is still a lot of work, so we chose to simplify the mechanism to include 4 planets: Earth, Mars, Jupiter and Saturn. This leaves us with a 7-gear train, plus 2 extras to drive the counter, which I'll explain later. With Alistair's help cutting the majority of the gears, it felt like this was a project we could actually manage, and an opportunity to practice some new techniques for the ongoing Watch project. Alistair made these gear cutters especially for the project. Even though they are made from tool steel, they can still safely run at speeds of 3000 RPM in brass with no problem. Now for last month's Patreon video, I restored this lever carriage for projects just like this. A lever carriage is perfect for gear cutting because it allows rapid movement of the top slide when retracting the cutter after a tooth has been cut. Once set up, the process is pretty simple. The cutter is referenced against the outside of the blank, the depth of cut is applied, and each tooth is then individually shaped. In industry though, gears are not usually made like this, and a process called hobbing is preferred instead. Hobbing cuts all the teeth simultaneously, which is ideal for mass production. Once all the teeth have been cut, the wheels need to interface with other parts of the mechanism. This particular gear will engage with 2 off-center pins, so needs to be drilled accordingly. You may remember this piece of stainless from the IMI Trophy project. I'm going to recycle it here and use it to hold the largest gear in the mechanism for spoking. This gear is also called an idler gear. There are 3 idler gears in the mechanism that sit between each of the planets, and they have an important role. When 2 adjacent gears engage with each other, they rotate in opposite directions, and apart from Venus and Uranus, the direction of rotation of the planets is consistent. The idler gear sits between the 2 planet gears to maintain the direction of rotation. The other useful thing about the idler gear is that its size doesn't change the gear ratio, so we can use idler gears to specify the geometry of the mechanism. The reason this gear is so large is to maintain a good separation between the 2 largest planets. To hold the gears to their arbors, for this project I decided to experiment with Loctite 480, which I found is noticeably stronger than regular superglue. The other thing I wanted to try was cutting out the spokes using the pantograph instead of using a piercing saw and file, or coordinate milling, which are methods I've used in the past. The main challenge with using the pantograph is aligning the cutter with the centre of the gear. On large gears like this, lining up by eye is sufficient, but for the watch project I'll need to think of a more accurate approach. I decided to use this opportunity to experiment with some new finishing techniques. I tried rubberized abrasive polishers in the rotary tool, and they worked okay, but didn't seem to last for very long. I've been enjoying using this 3M lapping paper down to 3 micron, but after that I found it's best to switch to using a different technique to get a reasonable polish. Luxor with goat hair worked pretty well, as did radial bristle brushes. Suffice to say, there's still plenty to experiment with in the finishing department. Earth and Mars were fixed to their respective gears by drilling and tapping the gears themselves with 1mm threads and using standoffs situated underneath the dials. But Jupiter and Saturn were much larger in diameter than their gears, so Hazel designed a triad-like component to interface with the dials and the gears. This part can be made on a jig borer or a milling machine with a rotary table, and although I've used the pantograph for this project, you don't need one to complete it if you want to try it. We've uploaded all the drawings and CAD to our Patreon, along with an article on the design process if you want to try this project for yourself, or if you just want to learn more. This fluted knob can be used to drive the mechanism instead of the handle. Alistair made this counter for a Patreon project a while ago, but it's the perfect device to keep track of Earth days. There was no convenient way to attach the counter to the Earth gear, so instead we attached it to Saturn and geared it to rotate at the same speed as Earth. Each planet has 3 pointers associated with it to indicate sunrise, noon, and sunset. These will point to the longitude associated with the relative pointer, and the time between pointers is interpolated. Brass standoffs were machined to hold the pointers. This component represents Saturn's rings without obscuring the mechanism. So how do you actually read this clock? Let's imagine, for example, that we have a settlement on Mars, and they've set up camp near the Perseverance rover. We want to give them a call, and it's been predetermined that we want to schedule it for sunset on Mars. Firstly, the mechanism is rotated until the counter reads the number of days that have elapsed since the 1st of January. For the sake of argument, let's say the date we want to check is the 22nd of January. The Perseverance rover is located at 77 degrees longitude, so the device is rotated until 77 degrees aligns with the sunset marker on Mars. If we were based in London, we would have to make the phone call in the dead of night because the 0 longitude division on Earth is nearly opposite the noon pointer. If we were based in Sydney, we would have to make the call during lunchtime, and in Houston the sun would be setting at roughly the same time. Thanks for watching, and thank you to our patrons who make projects like this possible.